Hello and welcome to today's podcast. This episode is brought to you by BMIT, a trusted manufacturer and exporter of precision electrical test and measurement instruments. BMIT specializes in high-quality analog and digital panel meters, current transformers, shunts, and reliable electrical measurement solutions used across industries worldwide. Every safe and functioning electrical panel requires protection against leakage current. Whether in residential, commercial, or industrial environments, even small amounts of electrical leakage can create serious risks, including electric shock, fire hazards, and equipment damage. This is why earth leakage protection plays such an important role in maintaining safe and reliable electrical systems. In this podcast, we will discuss what an earth leakage relay is, how it works, its role in industrial electrical panels, how ELR connections are made, the key factors to consider when selecting an ELR, common mistakes to avoid, and how to choose the right protection solution for your panel. So let's get started. Every safe and functioning electrical panel requires protection against leakage current. Electrical panels play a vital role in daily operations across commercial, industrial, and residential environments. However, undetected leakage currents can become a hidden threat that compromises both equipment reliability and personnel safety. Even small amounts of electrical leakage can increase the risk of electric shock, fire, and equipment damage. This is where earth leakage protection becomes an essential safety layer for electrically powered systems. An earth leakage relay, commonly known as an ELR, responds quickly to leakage faults, helping protect people, equipment, and property while supporting compliance with electrical safety requirements. Because of this, ELRs have become an important component in modern electrical panels. Now let's understand what an earth leakage relay is and how it works. An earth leakage relay is a safety device designed to monitor electrical circuits for leakage currents. It operates together with a zero-sequence current transformer, often called a ZCT, or a core balance current transformer, commonly known as a CBCT. Under normal operating conditions, the current flowing through the phase conductors is equal to the current returning through the neutral conductor. However, when leakage occurs, a portion of the current flows to the ground instead of returning through the neutral path. This creates an imbalance. The CBCT detects this imbalance and sends a signal to the ELR. If the leakage current exceeds a predefined safe limit, the ELR reacts immediately. It activates its output contacts, which then trigger a circuit breaker. This is often achieved by sending a signal to a shunt trip coil or an undervoltage release coil connected to the main circuit breaker. ELRs are generally available in three main categories. The first is the analog ELR, which is simple, economical, and suitable for basic protection requirements. The second is the digital ELR, which offers advanced capabilities such as displays, adjustable settings, communication features, and fault logging functions. The third category includes integrated devices, such as RCCBs and RCBOs, which are commonly used in residential electrical systems. Depending on the application, ELRs can offer sensitivity ranges from 30 milliamps up to 30 amps. Now let's look at the role of earth leakage relays in industrial electrical control panels and systems. Industrial panels are often responsible for controlling heavy electrical loads, including motors, power distribution systems, pumps, and variable frequency drives, also known as VFDs. In these systems, earth leakage relays work alongside core balance current transformers to continuously monitor electrical currents flowing through phase and neutral conductors. When leakage occurs, the ELR quickly trips the breaker and disconnects the circuit, helping protect personnel and equipment. Modern digital ELRs offer several advanced features that make them particularly useful in industrial environments. They can provide alarms before a complete shutdown occurs, allowing operators to take corrective action before a fault becomes critical. They are capable of working with different waveform types, including AC, pulsating DC, and smooth DC loads. Many digital ELRs support communication protocols, such as Modbus, making integration with PLC and SCADA systems easier. They also offer event logging capabilities, which support predictive maintenance by helping maintenance teams monitor system performance and fault history. Now let's discuss how Earth Leakage Relay connections are typically made. Proper installation is essential to ensure reliable operation and safety. The first step is connecting the auxiliary power supply. The supply is usually connected to the A1 and A2 terminals of the ELR. Most ELRs can operate with AC or DC voltages ranging from 110 to 240 volts. Next comes the CBCT connection. The secondary wires from the CBCT are connected to the T1 and T2 terminals of the relay. An important installation rule is that only the phase and neutral conductors should pass through the CBCT window. The earth conductor should never pass through the CBCT, as this can interfere with proper leakage detection. Another critical part of the installation is the trip circuit. The ELR output contacts are connected to the shunt trip coil or undervoltage release coil of the molded case circuit breaker, commonly known as an MCCB. When leakage current exceeds the set threshold, the relay activates and opens the trip contact, disconnecting the circuit to maintain safety. Most ELRs also include a test button, which allows routine verification of proper operation. Regular testing helps ensure the protection system remains functional and reliable. Now let's look at the key factors that should be considered when selecting the right earth leakage relay for a panel. Choosing the right ELR requires an understanding of the load, system design, and protection objectives. The first factor is sensitivity, also known as trip current. This determines the leakage current level that will trigger the relay. For personnel protection, 30 milliamps is commonly used. For fire protection, settings between 100 and 300 milliamps are often selected, while industrial applications may require values up to 30 amps. The second factor is time delay. Time delay settings help prevent nuisance tripping caused by temporary or transient currents. Depending on the application, delay settings may range from instantaneous operation up to 10 seconds. The third factor is the relay type and waveform compatibility. The selected relay should match the type of load being protected. Applications involving VFDs may require Type A or Type B relays capable of detecting more complex waveform characteristics. Another consideration is the auxiliary supply voltage. The relay's operating voltage should match the available site supply. The CBCT size is also important. The CBCT window must be large enough to accommodate the cable bundle passing through it. Many users also evaluate advanced features such as Modbus communication, alarms, diagnostics, and event logs. These features can significantly improve monitoring and predictive maintenance capabilities. Finally, consideration should be given to mounting requirements and environmental ratings, including DIN rail compatibility and protection ratings suitable for industrial environments. Now let's go through a structured approach for selecting the right ELR. The first step is to study the load type. Determine whether the load is purely AC or contains DC components, such as those found in electric vehicle chargers or variable frequency drives. The second step is to define the protection objective. For personnel safety, 30 milliamps is generally recommended. For equipment and fire protection, settings between 100 and 500 milliamps may be more appropriate. The third step is selecting the proper CBCT size. The window size should match the cable bundle that will pass through it. The fourth step is determining the appropriate time delay. Fast tripping is generally preferred when personnel safety is the primary concern. The fifth step is verifying the auxiliary power supply to ensure the relay can operate correctly under site conditions. While selecting an ELR, it is also important to avoid common mistakes that can compromise protection performance. One common mistake is using an undersized CBCT. This can create measurement issues and lead to unnecessary tripping. Another mistake is using an AC relay in systems where DC leakage may be present, such as installations with VFDs or electric vehicle charging systems. Incorrect time delay settings can also create problems. Delays that are too short may result in nuisance tripping, while delays that are too long can reduce protection effectiveness. Improper wiring is another issue. Running the earth conductor through the CBCT can make leakage detection inaccurate and reduce system reliability. In TNC systems, using earth leakage relays without proper protective earth-neutral separation can increase leakage-related issues. Regular testing and inspection of protection devices are equally important. Without routine verification, hidden faults may go unnoticed until a real failure occurs. By avoiding these common mistakes, you can ensure that the protection system performs exactly as intended whenever a fault occurs. That brings us to the end of today's podcast on how to choose the right earth leakage relay for your panel. Selecting the right ELR is an important step in building a safe, reliable, and compliant electrical system. From understanding leakage detection and CBCT integration to selecting the correct sensitivity, time delay, and relay type, every decision plays a role in protecting people, equipment, and operations from electrical faults. Thank you for listening. If you found this episode helpful, please like, share, and subscribe for more informative content. To know more about BEAMIT and its range of electrical measurement and protection solutions, you can visit our website at beamit.com. Let's wrap it up here. Thanks again for listening.